Welcome everybody to this week's Ask an Astronomer live stream. My name is Stefan Hammersheim. I'm here with Andrew today, and we are PhD students at the Institute of Astronomy at the University of Cambridge. And we're here to answer all your questions about science, the universe, and everything. So maybe to start, Andrew, do you want to introduce yourself and say a bit about what you're working on?
Hello again. It's good to be back on the Ask an Astronomer stream. So yes, I'm Andrew. As Stefan said, I'm a PhD student, and I work on protoplanetary disks, which hopefully are appearing on the screen next to me now. So protoplanetary disks are basically what we think of as the sites of planet formation. So when we form a star, there is a big cloud of material which collapses and forms lots of stars, indeed whole clusters. But there's some leftover material, and that ends up orbiting the star in the shape of a disk. And these are the environments that I study. Now, one important question for those, of course, is when do the planets actually form? That's something that a lot of work's been going into. And I think one of the kind of big revolutions of the last few years of this is that more and more evidence is pointing towards the fact that these disks form early. And the planets in them form very early, rather than perhaps at the times that we're seeing. And that's because, like in the pictures we see here, we often see that these disks are not completely smooth, like some sort of dinner plate, but they've got all these gaps and rings in them. And we think that those gaps are created when you have a planet orbiting in the disk, and it clears the material from around its orbit. And it can also trap some material outside of it, leading to those bright rings. So although there's not always a perfect one-to-one correspondence between the gaps and the planet, that's roughly what we think is happening. So as I say, I work on these environments. I particularly work on understanding how we can get rid of these disks. So if we heat up the surface of these disks, we can heat all of the gas in the disks to quite a high temperature, and that causes it to be blown off basically in a wind. I also work on looking at how the dust, which is actually what you're seeing in these photos, is small grains of dust, how that evolves in the disks, and whether that ends up on the central star or blown away in the wind, or perhaps more tantalizingly, it would form a planet like the Earth.
Yeah, so you can ask Andrew all the questions that I have no idea about. And while you're talking about questions, we already got a few questions from today. Thank you, Bella, for sending all the questions. So we got one question about how a mirror kind of works with light, so how a mirror bounces light, and how the gas makes the sun have its own light. Maybe, Andrew, do you want to say something about what's kind of the difference between things reflecting light and like things like the sun that create light themselves?
Yes, sure. So some things, as you say, create their own light, and as the question says, the sun is one example. So in the sun, what's happening is we have a large amount of gas. It's quite a lot more than the Earth. Say Jupiter, the largest planet, is about 300 times more mass than in the Earth, and the sun is another 1,000 times bigger than Jupiter. So we're talking 300,000 times what there is in the Earth. And most of that is hydrogen. And hydrogen is the simplest element in our universe. And at the center of the sun, the density and the temperature are so high that you can basically squash these hydrogen atoms together so that you start forming helium via a number of different nuclear fusion processes. But in so doing that, because you've kind of brought stuff together, that's a bit of a more efficient way of packing stuff in. So that actually releases some energy, basically in the form of light. Now, this light, actually, I think one of the incredible things is, one of my incredible facts about the sun, I always think, is that it takes about 8 minutes for the light to get to the Earth from the surface of the sun, but it can take something like 1,000,000 years for it to actually get out of the center of the sun, because the sun is so dense that the light can bounce around on its way out, and it keeps being scattered off atoms and absorbed and re-emitted. So this leads me to then talk about what can happen in other ways. So here, the light from the sun is originally coming from this nuclear reaction in the center. But as I say, what it can happen is it can be, say, absorbed by an atom. And that basically excites the atom. It might cause it to move an electron about inside the atom. And at some point, the atom thinks, I'd actually like to relax back to that lower energy. And so that electron drops back down and it emits the excess energy, just like it absorbed out again as light. So that's one process that can go on. And so if we looking at the surface of the sun, that light has been processed all the way through. And basically, because the sun at the surface is very hot, it's 5,000 to 6,000 degrees, we can see that glowing. It's just like if you get a piece of metal, a pan in the kitchen or something, and you were to heat it up very, very hot. So you see this metal working or something like that, welding irons. As you heat it up, it begins to glow red hot. And that's what we begin to see in stars. We see that some stars are glowing in basically a red light. And as you heat it up further, it would become white hot. As you heat it up even further, it becomes sort of blue hot. So we have stars with a whole different range of colors, right from the red ones, which are the coolest, and the blue ones, which are the hottest, kind of opposite of what we actually often think about with how we label taps or something. So in terms then of what reflection is, well, reflection is where a particle of light, so a photon, comes and hits something and just turns around and goes back. So that tends to be that basically there's nothing good at absorbing it there. So it's just kicked back basically in the direction it came from, or if it came in at an angle, at some other angle, but it's not able to pass through. Whereas say in something like the sun, we're getting a lot of light sort of all bouncing around on the surface, and eventually it's being heated up because it's glowing hot. So whereas in a mirror, it's just the light bouncing off you, bouncing off the mirror, and say back into your eyes. Or indeed in a telescope, of course, telescopes that we use to observe the universe. A lot of the big ones are used professionally are reflecting telescopes. So you have a mirror, and the light coming from something like the sun or a star that is glowing with its own light comes and hits the mirror and then goes into our cameras or our eyes. And of course, the way that we see planets, again, is because the light from the sun is traveling all the way to, for example, Jupiter is quite bright in the sky in the middle of the night at the moment, and reflecting off Jupiter, and again, traveling all the way back into the inner solar system, into our eyes. So that's kind of the basic difference, is whether it's creating its own light or whether it's reflecting that light from somewhere else.
So basically everything we see is, well, almost everything we see is not creating its own light except for stars, right? All the light that we see eventually came out of stars. Like the moon, etc. is all just light from the sun. That's
yeah.
really cool. We got a question on YouTube. How did the moons of lava planets, so Jupiter and Saturn, form? And how does it differ from the formation of our own moon?
Oh, that's a great question, because I think there's actually lots of different ways that these things can form. So our own moon, it's generally accepted these days that it formed when a small, probably Mars-sized planet, which is sometimes known as Theia, crashed into the very early Earth. We're talking about this happening about 4.5 billion years ago. And in so doing, basically, it knocked off a chunk of material, which was then caught still orbiting the Earth, and gradually that coalesced and formed the moon. And there's evidence from the rocks and the chemical composition and those kind of things as to how that happened. If we go out to Jupiter and Saturn, they've each got in excess of 60 moons. And so in that case, there's actually quite a large range of ways that some of them could have formed. I think the biggest ones, so for example, around Jupiter, the 4 big moons, which were discovered in the 1600s by Galileo Galilei, they were Ganymede, Io, Europa, and Callisto. And those 4 big moons probably formed much the same way as planets do around a star. So as Jupiter was growing, just like when a star is growing, I talked at the start, it would have a disk around it. In this case, we'd call it a circumplanetary disk because it goes around a planet. And in that, you could get clumps forming, and those clumps would form some of those larger moons. But it's still an certainly ongoing process to understand exactly how did they get their compositions that they have. So, for example, Europa we see is very icy. It's got an ice surface, and we think probably from gravitational influence and the cracks that we see in the ice on the surface, it's probably got a liquid water ocean underneath that ice. So that's obviously quite exciting for living for life. So we're still trying to understand, I think, how exactly all of those things got to be exactly how they are. But other ones of them could have formed basically like large asteroids or dwarf planets and then been captured into orbit. And that tends to be, well, the clue to that tends to be if we see them going backwards around the planet compared to most of the other moons or the way that the planet spins, that implies that they didn't form there from everything rotating with the planets, but they were captured in. Or if they're on very inclined orbits perpendicular to everything going around in a single plane. And then you've got, I guess, sometimes you could get them formed between collisions with each other. I guess so. There's definitely some which I think it's Miranda, which is a moon of Uranus, shows a really kind of scarred surface as if it's broken apart and been put back together again. So there's lots of different things that could have gone on there to create these. So it's kind of a case probably of looking at each individual moon and trying to say, how big is it? What's it made of? What's its orbit like? And trying to piece together that history of where it came from.
So when the moon, so the moon of the Earth, for example, formed, does it still look like this disk that we have here on the picture? Or was it already more kind of normal, more like today?
No, so I think by the time that the moon formed, I think a lot of that would have kind of dissipated, started to clump together. I mean, it's always a little bit of a grey area where you draw the lines, because the reason that we often think of something as a protoplanetary disk, like I study, is because it tends to be very gas-rich. But as I say, at some point that gas disappears, whether it ends up on the star, whether it forms a gas giant like Jupiter, or whether it's blown off in a wind. But what we do see around some fairly young stars, not as young as the ones in the photo. I mean, the one on the left there is probably less than 1 million years old, to give you some indication. What we see around ones that are maybe up to 1 billion years old is that you have what we would call a debris disk. So at this point, you've got rid of all the gas, but you've basically still got significant asteroid belts and lots of planetesimals, as we call them, kind of building blocks of planets, and small planets. But often these, because there's been a lot there, because the system's still settling down, it can be quite unstable. So things can be moving about, things can be shifting. So if you look back in the moon's early history, we see a lot of craters, and we can use techniques to try and guess the ages of those craters. And there's a huge number of craters from really early on, and then the number of craters kind of drops off. And so this gives us an indication that there was something called the late heavy bombardment, when there were lots of asteroids flying around and basically impacting the moon, and they would have been impacting the Earth as well, and also gas giants like Jupiter. And this has gotten rarer as time goes on. But I think, although that probably would have been happening in a protoplanetary disk, that's something which would have happened kind of comfortably after its end.
Yeah, you were just talking about Pluto, or you were talking about Charon. No, you were talking about Miranda. Anyway, we got a question about about the Pluto-Charon system. So Pluto is the former ninth planet that is now no longer a planet, and Charon is its moon, if you can call it that. And yeah, we got a question about how the system works and how they're facing each other in the same way.
Yes, so as you kind of hinted at there, one of the weird things about that system is that Charon is actually very large compared to Pluto. So I can't remember exactly what its mass is in comparison, but it might be as high as a third or something off the top of my head. And that actually means that rather than it really orbiting Pluto, they're kind of both going around a center point in between them. I mean, technically that's true of the Earth and the Moon, but the point is so deep inside the Earth that you can't really tell. So that system, I guess, yeah, something like that is quite hard to think exactly how it would form. Maybe I think the most likely thing is probably some capture event off the top of my head, rather than those two things coalescing out of some swirling thing that's already going around each other.
So capture means that some object flew past Pluto and then kind of got caught by it?
Yeah, exactly. So if the two got close together but not quite close enough to collide, then if Charon were flying past, it could be kind of bent by Pluto's gravity and basically captured into orbit, so that the two ended up orbiting together when they were once separate. So I think the second part of the question asks about kind of them facing each other in the same way. And again, I don't know the exact details then, but certainly with our own moon, we always see it presenting the same face to us. So as it goes around, it's always pointing the same side towards the Earth. And that's all to do with angular momentum. So basically how much something is spinning. And this links into the idea of tides. So we see tides on the Earth, which are largely due to the moon's influence, basically pulling up a bulge of water, because water is really easy to deform, whereas rock isn't. So you see this bulge of water traveling around the Earth twice a day as the Earth rotates, and that's why we get tides. But the Earth also has that effect on the moon, and because it's pulling slightly stronger on the near side than the far side, there is a difference in that pull, and that does stretch the moon slightly. And basically, although it's much harder and there's no water in the moon, you do get a much smaller tide effect in the rock. And that gives you something which just likes to line up pointing the Earth. Because if it gets a bit far ahead, it's kind of like a lever being pulled back. And if it goes the other way, a bit far behind, it gets pulled back to the center. So you basically end up with something where you've got a bulge that's just facing the Earth. But actually, in order to do that, what you've done is changed the moon's orbit at the same time. So as the moon has ended up locked to facing the Earth in the same way, it's actually moved apart. And that process is still slightly ongoing. So it moves something like 3 or 4 centimeters away from the Earth every year. So if that were to carry on, eventually the moon would get far enough away from the Earth, it would drift away and go into orbit around the sun. So, you know, these systems, even though they can be seen quite stable, they can actually be changing on very long time scales even still.
Very long time scales. Depending on who you talk to, might be billions of years or millions of years or thousands of years. But yeah, certainly, as astronomers, we always have kind of a relatively long time scale in mind, I would say. Talking of things being slow and fast, we got a question about how light is traveling so fast. I think that's actually a really nice question, because it kind of asked, like, why does light travel at all? So why do kind of waves in general travel? And I think what's a nice thing you can imagine, what you can think about is, if you have, like, let's say, just imagine some lake, and you make a wave in that lake. The wave will travel over, like, some distance. And the reason is that you kind of, you move up the water at some point, and then it moves up the water next to it, and then the water next to it, etc. So it kind of propagates. And because the water is kind of connected. And the stronger this connection is, the faster this happens. So when you think about sound, so let's say you make a sound underwater, then the sound will travel, because all sound waves are also just kind of pressure waves. So they kind of move the water, they squash and extend it a bit. And then this will kind of travel through the water. But when you look at, let's say, some metal, let's say you go on next to the road, there's this metal thing, and you make a sound on this one, like on metal, the sound travels much faster, because the connections between the metal atoms are much stronger. And now, light doesn't work exactly like sound, so it's not pressure waves that travel, but it's electromagnetic waves. So it's electric fields and magnetic fields that kind of oscillate back and forth to go on and on. But the idea is the same as for normal waves. So you have some stretching and some movement in the electric fields, and then this makes the fields next to them move, and the fields next to them, etc. And because those fields are so strongly connected, light moves that fast. So you can actually compute the speed of light just from knowing how well the electromagnetic and the electric and the magnetic fields are coupled. And yeah, that's how you get to the 300,000 kilometers per second speed of light, which is really fast. If you're looking at anything like Earth, but if you're looking at astronomical systems, it doesn't seem that fast. So if you look at the sun, as you just said, 8 minutes for the light from the sun to the Earth, a few years from the nearest stars to us. So yeah, light is, let's say, relatively fast.
I think there was another nice question about light there, which was, as well, if it enters a black hole, will it bend or stretch like other things do? And the answer to that is, quite simply, yes, it does get bent. So this is the idea behind gravitational lensing, for example, which I'm sure Stefan has a slide of, I think, somewhere.
Yeah, I'll take some picture.
But
there we go.
So what we have with that basically is that the idea of a black hole is that space-time is getting very strongly curved. So it's a bit like being on the surface of the Earth, where if you walk in a straight line, it seems like you're just walking on some rectangular grid of your map. But eventually, if you were to walk in a straight line far enough north, you would come to the North Pole. Whereas if you walked 100 miles east and then turned around and pointed directly north and walked directly north until you hit the North Pole, you'd also end up there. So these different paths that you think should be separate end up coming together, and that's basically the idea behind Einstein's theory of general relativity and how gravity pulls things together, that you have what are straight paths on the surface, say, of a sphere come together. What a black hole does, or in fact any object in a weaker sense, is bend space-time so that the idea of a straight line is not quite as simple as we'd think, but it's a straight line and something else. And I guess one of the first facts we often learn about light as it travels in a straight line. So it keeps traveling in what it experiences as a straight line, but on a kind of wider scale, that's actually curved. And so what that does do is it does bend it around a very massive object. So in this case, what we're going to have here is some sort of galaxy, I'd imagine, in the foreground, maybe a small cluster of galaxies, and you've got another galaxy sitting behind it. And as that light comes near the galaxy, that total mass of all of the stars in the galaxy, the black hole, any of the dark matter, bends the light around the galaxy just a little bit, but enough that rather than heading off in some cone, it starts to come back in and starts to head in towards us on the Earth. So what we get there then is this nice ring where from all sides it's being focused back in towards the Earth. But actually, this was first observed not with quite such deep things, but with stars. So in 1919, there was a total solar eclipse, and a few teams went to different parts of the world basically to ensure they got some clear skies and watched this eclipse, and they measured where the stars would normally be, and then when the sun was covered by the moon, they could measure where the stars actually were, and there was a deflection because of the gravity of the sun bending the light rays that were coming very, very close to its surface. So there was that small effect there. So actually, we do see that effect of light being known. It's been known, I guess, for just over 100 years.
That's impressive. So when the stars were kind of behind the sun, they looked like kind of like in this picture, kind of not in the place where they should be, but at a slightly different place. Although not that impressive, as here, I suppose.
Yes, I mean, they wouldn't have seen a ring because it wasn't like they were looking at one sort of directly behind, which is when you, or closely behind, it's when you tend to get that. They were looking at the ones which were still to the side of the sun, but just displaced from where they should have been normally.
Yeah. I think when you would have a black hole, you could see this effect quite strongly. And I think I have a simulation of that here. This would, like, if you would have a black hole really close to Earth, you could see like all these stretching in really a lot of detail. But I'd rather not have this black hole that close to Earth because black holes aren't that friendly when you're close to them. They make you all stretchy and spaghettified and make time run slower, so that's a whole lot of mess going on.
I mean, I guess the equivalent of stretching light in a black hole, to answer the other detail in the question, is would be gravitational redshift. Would you agree?
Yes.
So, do you want to explain that?
Wait, no, it would blue shift, right? So,
well, depending which way.
Yeah, right. So, one thing that happens to light when it comes into a gravitational potential, so when it comes to close to something that is heavy, like the Earth, like the Sun, like a black hole, is that it changes its frequency. So, what you can imagine essentially is that, the closer you get to some heavy object, the slower time runs, and the faster the oscillations of light look like. So it looks like the light the frequency of the light is increased, and the wavelength, so kind of the size of one oscillation of wave, is shortened. And that also means that it has a higher energy. So that's kind of what happens to all light everywhere where there's gravity. And of course, if you would have a black hole, this effect would be especially strong. And the light that you would see, kind of, if you were inside the, like, outside the black hole, you wouldn't notice, because the light would fly close to the black hole, would get blue shifted, so it would get a shorter wavelength. and then comes out of the black hole, or not out of the black hole, but kind of it gets close by and it comes back to us, and then it gets reversed, this effect, so you wouldn't notice anything. But if you would be kind of sitting, well, close to the black hole or even in the black hole, you would notice that all the light that's coming at you is suddenly much bluer than it used to be. But that's another really cool effect of black holes.
There was actually a really cool paper about this recently, which calculated whether you could have a planet orbiting just close to the event horizon of a black hole. So that's the point of no return. Once you cross that, you're not coming out. And if it were orbiting there, the blue shift of basically just the general radiation that is around our universe, known as the cosmic microwave background, would actually be kind of the right temperature to get liquid water. And so there was a sort of very narrow range for the right size of black hole, the right conditions. You could just about have a habitable planet for something like 10,000 years before it cooled down too much. So you can get some really cool, kind of bizarre things out of that.
That would be interesting. A planet where you could live within, like inside the black hole. You just can't get out. Okay. Yeah, while we're talking about black holes, we got also the question about white holes, which are kind of hypothetical objects. So the question was, what is the difference between a white hole and a black hole? And there are two quite different objects. Well, they're also similar. Black holes are objects that are really heavy, and they exist. We know they exist. And the special thing about black holes, and also why they look black, is that if something falls into a black hole, it can't get out anymore, not even light. As one of the chat messages said, a black hole is like a vacuum cleaner. I think that's pretty accurate. So if something comes within this kind of Schwarzschild radius, so this kind of radius where nothing can escape, as soon as something is in there, it doesn't get out, even light. And there's kind of the hypothetical idea of you could have something like a white hole where nothing comes in, but everything comes out. So there's some object where our mass, energy, whatever is coming out of all the time, and there's no way to get in. I mean, this would have to be connected in some way to maybe a black hole or something. So, I mean, you have to produce the stuff somehow. And it would also be quite obvious if there were these white holes anywhere close to us, because we would see suddenly a point where lots of light is coming out. But it's just an idea, and we haven't observed any such thing, and we don't expect it to exist. But of course, it would be a really cool thing. It's also related to wormholes, by the way. So you got a question about what proves that a wormhole might exist, but not has happened yet. Do you want to say something about that, or should I?
I mean, I say what I can. You can probably say a bit more than me. But yeah, I think basically, as far as we know, our theories, our mathematical theories that describe, say, general relativity, describe space and time and gravity, could allow you to have something where you basically fall into what's like a black hole at one point and you come out somewhere else, a bit like a white hole. And there's no kind of reason that we know of within our theories why that couldn't happen. So I guess you could theoretically disprove it mathematically, but nobody has. But we've not seen any evidence for one. I mean, we've seen indirect evidence for black holes, like the picture that was taken just over a year ago, but we've never been able to visit one and actually find out what happens if you go through one. So there's no evidence for these things. So they could be there. You can't really prove that they do exist, but you know, it's open to there being them, I think, in my opinion, at the moment. I don't know what your opinion is, but
yeah, I think the one point that you made was really good, that you can't prove that it is there, and actually, like, it's really hard to prove that a theory is right, or in a certain sense kind of impossible. Like we think, okay, general relativity is probably right, and I mean it works quite well, and it could probably allow wormholes, but there's no way to prove that actually it is right, because one day it might just be, oh, something happens and we have no idea how to explain it with general relativity, and we have to kind of add another rule to our theory. And there's always a way to prove a theory wrong, right? If you look at the Mercury, you can prove, okay, Newton's theory of gravity is wrong. End of kind of sentence. But when you want to show that something is right, you can't do that. You can just say, okay, it's right until now. It hasn't kind of been disproven. There have been no known problems, but we don't know if it's actually true. So that's kind of something that you can never find out really.
Yeah, Newton's theory of gravity had been working well for 200 years before really there started to be these holes in it that general relativity filled. And there are plenty of things we don't understand about our universe at this point. So people are constantly searching for the next thing that just goes a bit beyond relativity, aren't they, to see what we get.
I mean, saying that we understand our universe, or we have things like dark energy and dark matter, and we have no idea what they are, is maybe also a stretch. But yeah, that's actually the exciting part about science, right? There's still mysteries to be solved.
Definitely.
Yeah, that was another related question to the wormhole. So I think it was about how they form, or maybe what happens if two black holes collide. So actually, that's a question I can answer. When two black holes collide, they just form another black hole. I know it's boring, but that's what happens. We did actually observe this with so-called gravitational waves. Maybe I'll say a bit about this in a second. So yeah, when you have two black holes, they just attract each other like any other massive objects. And then when they're really close, usually when you have like a kind of binary star that has been born together, and they have two stars, and they burn out eventually, and eventually they both form black holes, and you have two black holes orbiting each other, and they orbit and eventually get closer and closer together. And when they get really close, they just merge into one black hole. And whatever happens in the inside, we have no idea about kind of what is going on there, because it's a black hole, so we can't look inside. There's nothing coming out. So whatever might be going on inside, we don't know. I mean, okay, there could be some wormhole stuff going on, but I don't think that's like realistic in any way. I don't even think there's a theory proving like suggesting this even. Yeah. So right, and what they do with these black holes is when they orbit each other, is send out gravitational waves. So that's kind of waves actually in space and time. So what these gravitational waves do is they stretch and what was the other one? They make space kind of grow and shrink a bit. So what you can imagine is if you go on Earth and you have a stick that's 1 meter long, and a gravitational wave passes through you, then the stick will for a short while grow a bit over 1 meter and grow a bit smaller than 1 meter. The problem is that this change is super, super tiny. Like it's much less than a proton diameter or something. It's barely detectable. So what people did is build gravitational waves observatories, and what they do is take really long, well, let's say sticks, actually they take lasers, that are 4 kilometers long, and really, really accurately measure how long they are to kind of detect these gravitational waves, which is really impressive. We got another question on YouTube. Is it possible to see the planets with Skywatcher Heritage 130p? Because I can't find them. I can see the moon and stars. I suppose.
Do you want me to?
Yeah. Yeah, go ahead, Andrew.
Yeah. So, yeah, the answer would be yes. So that's a kind of, well, so the 130 there means that the mirror at the back of the telescope, as I think it is for that sort, has a 130 millimeter diameter, so that's 13 centimeters or about 6 inches. And so that's the kind of detail, basically how much light you can get, how faint a thing you can see. And that's good to see quite a lot of the sort of stuff you're going to want to look for. In fact, if you go out at something like 3 a.m. at the moment, because as I say, there's a comet out at the moment which has been attracting lots of people to go out at that sort of time, then you could look out and you can see at the same time Venus, Mars, Saturn, and Jupiter all quite easily without a telescope, just with your eyes. So the telescope, what that's going to do is it's going to magnify the picture, and that's going to make them easier to see. And a telescope of that size is going to be great for looking at those. So you should be able to find information online. There will be, I'm sure, websites of lots of the popular astronomy magazines like Sky and Telescope or The Sky at Night or Astronomy Now. All of these kind of places will have charts of where the planets are going to be, so that you can find them amongst the stars and work out what they are. But they, particularly Jupiter, tends to be really bright. And in a telescope of that size, you won't just see Jupiter, but you will see its 4 brightest moons. So the ones I mentioned earlier, Ganymede, Io, Europa, and Callisto. And again, you can always find apps for phones which tell you which moons are which. There's quite a good app called Night Sky Tools that contains, again, all this information about when the planets will be up, which moons are which for Jupiter and Saturn. And also, if you get the program called Stellarium, which is available for download free online, that allows you to change the time on there, change your location, and look at what the sky would look like. So it's great for just exploring and saying, okay, what the sky looked like from the other side of the world, or you can even do it from another planet or something. But you can set your time to when you'd like to go out and see exactly where they'll be, so that you know which direction to look for the bright thing. So that's a good way of finding these things. And there's just been a follow-up question there. I see that, are they close to the horizon? Well, as of a couple of nights ago, Mars was pretty close to where the moon was, and that was pretty decently high. Obviously, how close they are to the horizon is going to depend on exactly when in the night you look at them. So I think when I went out at 3 a.m.-ish to look for the comet, Venus was not that long after rising, so it was relatively low, and Jupiter was starting to get towards setting, perhaps. So that was getting a bit low behind a house. But yeah, there's going to be there's definitely going to be a time that they're nice and high if you pick the time right. And again, the charts or the apps will help you determine that.
Yeah, you were just talking about the comet, so I picked out the picture that you sent me, that you took from the comet actually.
Yes, so this is when I went out a couple of nights ago, and this is not by any means a professional astrophotographer. Go and search on the internet, because there's hundreds of interesting comets out there, and photos of this comet. But it's really impressive. It's the most impressive one I've certainly seen in my lifetime, at least since I've started being into astronomy and looking for these things. So, and as I say, it's quite low in the north, so you do need a decent northern horizon, but it's visible late evening, sort of 11 to midnight, certainly. It's visible around 3 a.m. And you've got this beautiful tail extending upwards from it that you can see in this photo I took. And that's basically where lots of the gas and dust has been coming off the comet. And I don't think you can really see the gas here, but in terms of the dust, that's basically being left behind, a trail of dust, as the comet sort of disintegrates as it's heated up, because it went past its closest point to the sun about a week ago, I think. So it's really quite bright at the moment. It's really quite special and impressive to see. So you just have to look north. As you can see, it was beginning to get light in the sky here. So yes, this is comet Neowise, as somebody's pointed out in the comments. And so it's fairly easy to see this kind of this smudge in the sky. Question, will it still be here on July the 31st? Well, I don't know exactly, but I think it would be. I think it's going to be moving through the sky, getting easy to see in the early evening, probably fainter as it moves away from the sun, but I think it will be around for some time yet, a few weeks.
Okay, there was such a discussion going on in the chat about Jupiter, and actually lots of things about Jupiter. So maybe let's start with the core. Well, discussion if Jupiter actually has a core as a gas planet, or if there's anything like a core, or if it's just like kind of gas all the way through.
Yeah, so I was quite interested watching those comments. I can't say it now. Let's talk about the comet. So yes, the interior of Jupiter is obviously quite hard to probe, because it's too dense. If we send a spacecraft in there, that they tend to get destroyed by the atmosphere. So it's very hard to know what's going on inside. And actually, the best information we have, so a really interesting talk about this a couple of weeks ago, is we send probes into orbit around Jupiter, and by tracing accurately their orbits, we can see how the gravity of Jupiter is changing. And that actually gives us some idea of what the internal structure of the planet is like, how it's rotating and things. So we're kind of beginning to understand the interior a bit more, but we do think that perhaps a planet like Jupiter, when it would have formed, for example, in a protoplanetary disk like we had earlier, would probably have started with a very rocky core. That tends to be what we think it's easiest to put together first. And perhaps it would get to something like 10 Earth masses of rock before it starts to pull a lot of gas in. So at that point, it kind of undergoes possibly this runaway gas process where more and more gas piles on. And so Jupiter ends up with 317 times the mass of the Earth, and perhaps 10 to 20 Earth masses of that. So, less than 10%, 5%-ish is kind of solid material. So unlike the Earth, where most of the mass, most of the matter is solid rock, and you've just got a thin layer of atmosphere. So it's kind of ends up with a very different composition. Probably does have something rocky like the Earth, very deep at the center. But there's also been some discussion there that we also think that there could be this layer where the pressure of the gas, in particular the hydrogen, gets so dense that it kind of ends up in this liquid state, just like we get liquid water on the surface of the Earth, I guess. And actually, that allows it to be magnetic. And we do see that Jupiter has very, very strong magnetic fields when we have spacecraft flying by it. We can measure these magnetic fields, and I think we probably have seen aurora on Jupiter. We've certainly seen them on Saturn. So we think that there's definitely something, likely to be undergoing this process inside. So yes, we tend to get a lot of this information by going to orbit. It's very difficult to get from here. But as I say, it's an ongoing field of study. As so many things are, we're always trying to learn more. So
I like the recent comment. It's not a failed star, it's just a very successful planet. How much heavier would Jupiter need to be a star?
So it does need to be it needs to be about 10 times bigger than it is. So what we have stars, which I mentioned earlier, are shining under their own light because they can undergo this fusion process in their core. And then we have planets which are just reflecting. And somewhere in between, we have what are called brown dwarfs. And if you remember that I said the Sun was about 1,000 times more mass than Jupiter, so about 1,000 times as much stuff. And basically, if you go about more than 10 times smaller than the Sun, the conditions don't get hot and dense enough for you to fuse the hydrogen. So it can't kind of burn. But if you can kind of do some other things. So sometimes you hear about heavy water, which is water where you've replaced the hydrogen, so water being H2O, so it's 2 hydrogens and 1 oxygen, with something called deuterium, which is basically like a heavier version of hydrogen. The difference in the atomic scale is that rather than just having a single proton at the center, you've got a proton and a neutron. And so with something like that, that's actually a little bit easier to put together, because the most difficult thing about doing nuclear fusion in the Sun is sticking the proton and the neutron together. But we do have a little bit of that deuterium left over from the formation of the universe, which I'm sure Stefan would be able to tell you more about than I could. But that can start burning if you get more than about 13 times the amount of stuff in Jupiter. So there's that kind of range in between, and that's the things that we call brown dwarfs. So we have seen some planets that are a few Jupiter masses, but certainly Jupiter is quite an impressive one. We're finding a lot of planets these days that are kind of Neptune-sized when we look around other stars with, for example, the Kepler or the TESS missions. Yeah. So it reminded me actually of a comment that I once heard a lecturer say, which was that planets weren't failed stars, stars were failed planets. But then he is an exoplanet researcher, so.
Okay. Yeah, we got actually quite a few questions about Jupiter in there. So let's just take one more. That was about the surface of Jupiter. So kind of what's going, like, does it have like a surface? Is it just like it's just a gradual thing, or is there some well, not only like the core, but also some kind of layer where the atmosphere kind of ends, or does it just goes slowly from very thin to very heavy? And well, maybe something about the Great Red Spot, if you want to say something.
Okay, so to answer the first part, again, we don't fully understand the vertical structure, and there could be bits of it where you start to get almost like rain in the atmosphere. And the thing about atmospheres is there tends to be no kind of hard outer edge. Even the Earth's atmosphere, there's no hard outer edge. It just gets kind of more and more tenuous, weaker and weaker as you go out. But with something like Jupiter, what we're really seeing is the tops of the clouds. So that's kind of, if we wanted to measure the radius of a planet like Jupiter, we'd kind of be measuring basically where the tops of the clouds are. And certainly if we look for planets around other stars, again, you're looking often at if you want to know the radius, you have to block out some of the light from the star and measure how much you've blocked out. And so in order to block it out, you need to have something that's too thick to look through, like clouds. So that's kind of what we're looking at there, and that makes it very difficult to see, of course, what's underneath it. Just like if it's cloudy, of course, it's difficult for us to see out. If in terms of the storm, the Great Red Spot, well, we think it's a giant storm. It's been going for sort of 400 years. It's at least as big as the Earth. I say 400 years, could be more. That's when we started being able to see it, because we started being able to have telescopes to look at planets like Jupiter. So yeah, it's basically just a giant, really long-lived hurricane. But it will be to do with the heating inside the planet that kind of lets that happen, because I think I can't remember the exact detail now, but there's more heating going on from inside Jupiter than there is in Saturn, and so that is creating enough heat that can flow up, and the motions of that heat in the atmosphere allow you to drive these storms. Whereas we don't tend to see so many storms on Saturn; it tends to have a much sort of cleaner surface.
Yeah, we got quite a lot of follow-up questions in general for you, so you'll be talking for a while. We got a question about what the Oort cloud is up here. Well, it's already up.
Yes.
Yeah. But yeah.
So so earlier we mentioned the Oort cloud, possibly. So that's basically a collection of sort of asteroids or comets, and it probably exists at its inner edge, the kind of bits of it that maybe get very close in, at a few hundred astronomical units. So that's one astronomical unit being the distance from the Earth to the Sun. So a few hundred times that distance, then you've got some of these things which are beyond the Kuiper belt, which is kind of the second asteroid belt where Pluto is, and perhaps are kind of some inner members of this Oort cloud. But it's more a sort of hypothesized thing. But if it is there, it likely exists all the way out to something like 50,000 AU, so 50,000 times the distance from the Earth to the Sun, which is really quite significant. And the idea is that rather than being a kind of flat plane like the solar system or the asteroid belts, it's a big cloud of comets and things, and occasionally those get past each other and get disrupted, or at that scale, even a passing star can disrupt things, and comets can get kicked in from there, and they can travel all the way into the inner solar system, and that's where we would see a comet come from. I mean, the one that we showed on the screen earlier, that's got an orbit that takes a few thousand years. So that's probably, if it did come from that far, it's had its orbit affected by the planets as it came in, so it's not going out that far anymore. But certainly we get things coming in from there, we think, on these sometimes hyperbolic trajectories, which means they pass through once and then escape and never come back. So we definitely think that it's likely to be this Oort cloud out there, but it's so far away, and lots of these things are small. And even when I say these are comets, they're not going to look in our telescopes anything like we've got there, because as I mentioned, a lot of that is because material is coming off as the comet's heating. These are basically going to be icy asteroids. So all of that out there is just very hard to detect. So, but it's just like we were mentioning earlier with the formation of the moon and all these asteroids left over that were colliding with it in the early solar system. They're just some of the ones that have survived.
Yeah, you were talking about these programs that help you to like find stuff in the star a few minutes ago. Here we got a question on Slido about if apps like Skyview 3 are accurate for finding stars in the sky. I don't know this particular app. Do you know that one?
No, I don't know that particular one. As I know, Stellarium tends to be good. I use that myself, so I know that's reliable. But I imagine if it's out there, it probably is reliable, because if it weren't, it probably would have been stopped using and disappeared pretty quickly. So yeah, I imagine it is. Certainly, it's going to have the basic stars correct. The moon, you'll probably be able to tell whether it's in roughly the right place. And as I say, the planets are often bright enough that you can see them, but it's useful to point out which those things are. There's a free Google one for Androids and things. So there's lots of options out there.
Yeah, just as an example, like for something like Stellarium, which is like a free program, for your computer, you can like it shows you where different planets and stars are. At least in my experience, it was always quite accurate. Although of course I'm not an expert, I didn't look at the precise angle, but at least for like looking with a like little telescope, it's totally fine to use this.
Yeah, I mean, definitely it will allow you to see in the southeast there's a couple of bright things, that's Jupiter and Saturn, and then you'll know what the right thing to point your telescope is.
Yeah, right. We got one question about Oumuamua. What do you think Oumuamua is? So maybe you want to say first what it is, and then what you think.
So Oumuamua was something that we saw, must have been 2 or 3 years ago now, coming through our solar system like an asteroid or something. But when we looked at its orbit, like I mentioned, some of these comets sometimes come in and go past once and then leave the solar system because of the shape of their orbit. This looked like it had come from outside of the solar system due to its orbit. So it could have possibly come from the Oort cloud and been disrupted. But something about its orbit, I can't remember the exact details, but basically pointed to evidence that this was not from our own solar system, but it was from another solar system somewhere else. So this was our first example, we think, of an interstellar asteroid. I think there's been a second candidate since called Borisov, but this was this was quite exciting, obviously, because we've never seen this before. But this is quite useful because if we want to know how many things get kicked out of the get kicked out of the Oort cloud and then out of the solar system, well, if that process is happening in around other stars, we ought to know roughly how often that's happening if we know how often those things are coming through our solar system. So it's a nice way to kind of learn about what might be happening in our outer solar system just from what's happening in other places.
Yeah, so we got a question on Slido from the Kitten Lover, so I got a question as well. If I get stuck in a black hole, is there any way to come out? As far as we know, with our current knowledge of physics, there's absolutely no way at all to come out of a black hole once you're stuck inside. So our current theory tells you nothing, not light, not humans, nothing ever, no, not even information can come out of a black hole. So there's just the only way to stop this is not go inside. Just keep some distance from a black hole. And actually the tricky thing is, when you go black hole visiting one day, be careful, because you don't really notice when you get close to the black hole horizon, or even you pass it. Like without, if you check your I don't know, TV or your phone and notice, oh, it doesn't work anymore, well, then you might be inside. But like just by kind of feeling or looking outside, there's not really a way, like it doesn't really look much different from inside and outside. It's just that when you try to talk to someone that's, well, outside, then it doesn't work anymore. So because light is still getting to you, like you don't notice that nothing is going away from you because all the radiation and light is still coming towards you. So that's actually quite an interesting thing with a black hole.
Of course, you would notice if you started getting taller and spaghettified, wouldn't you?
That's true. So when there's a small black hole, so when you are close to the kind of center of the gravity, then the gravity at your feet is actually much stronger than the gravity of your head, right? Because your feet, well, when you're falling in the right way, right? So when the part of your body that's closer to the black hole will have a stronger gravity. So it will kind of get pulled into the black hole stronger than whatever of you is left outside. So what I think correct term for this is spaghettification. So you get stretched out when you get close to the black hole. And there was a similar question that I didn't miss about Hawking radiation and about if it contains information. So there's a thing that's called Hawking radiation, and that's, well, a kind of radiation that comes out of black holes. It doesn't really come out of black holes. It kind of gets created close to the surface of black holes. And as far as we know, it doesn't really have information. So it's just random radiation that's kind of coming out from black holes. And actually, that's one of the few processes black holes can die. So black holes lose energy, or they lose mass through this Hawking radiation. And we say they evaporate. So actually, the smaller black hole is, the faster the star goes. So if you have a normal black hole, this will take ages, like many times longer than the age of the universe for the black hole to die. But if you had a really small black hole, let's say you could make one in the lab, we can't, but if you could make one in the lab, it would evaporate within seconds. So wouldn't be dangerous. Okay, I think we're back to the solar system questions. So when you point your telescope at a comet, let's say this comet that you made a photograph of, could you see it actually moving? Like if you looked at it for, let's say, half an hour, would you notice that it moved in the sky, or is it too little to see?
Yes, I think you probably could. I've certainly, what you'd be having to do is just compare exactly where it was near to some of the stars. I mean, depending on how close it is to the Earth or to the sun will depend on how fast it's actually moving or how fast it's moving relative to us. But I certainly have looked through a telescope before, one of the big ones that we've got at the university in Cambridge. And I was there with a few friends and I had a look. And then when everybody else had had a look, I had another look. And it did look like it had moved a little bit. Not a lot. It hadn't completely left the field of view or anything. But you could actually see it moving. So that's it was slow, but yes, over a small amount of time, you wouldn't be able to kind of noticeably see it moving if you stood and watched. But if you compared half an hour later, you might sort of think that's not in quite the right place as it was before.
Okay. Yeah, just a few discussions in the chat about apparently if you could see some light that's like kind of close to like going out of a black hole or something. So I mean, what you could see is, let's say you have some I don't know, some objects, maybe a planet or maybe a piece of rock or asteroid or something would fall into a black hole, or yeah, actually what even happens on really large scales. So maybe I should say a bit about quasars. If my slideshow still works. So what happens when you have lots of matter that's falling into a black hole? So let's say like in this picture. So if there's a black hole somewhere and you have gas around it, this gas will fall towards the black hole, and it usually will form a disk for the reason that Andrew explained at the beginning, like its conservation of angular momentum. And this gas will heat up and it will emit radiation. So actually these black holes are really bright. So not the black holes itself, but all the stuff around the black hole is really bright, and these things are called quasars, and they're sometimes brighter than galaxies. Like they're brighter than the Milky Way in many cases. And they can be like emit lots of lights. It's just not the black hole. It's not something coming out of the black hole. It's just stuff falling into the black hole that's emitting the light. So that's kind of the effect that can give you light close to a black hole, even if it's not coming out of the black hole. Yeah, we just got the question, why is our supermassive black hole passive? So what you say is you can have active and passive black holes. Active are the ones which do this process a lot, so they collect a lot of material and emit a lot of radiation, and rather quiet ones that, well, don't do this process and are also less exciting, but also less dangerous, I would say. And our black hole isn't is quite passive. It doesn't do a lot. I don't know really why this is. Do you know, Andrew?
No, I mean, I think it would often, it's something again that people are studying a lot. I think it would often be fueled if you had a merger between two galaxies, then that can feed a lot of gas into the center and trigger something like that. But also, just depending on the age of the galaxy as well, if the galaxy still has lots of gas falling onto it, then that can be getting in towards the center and falling onto the black hole. But yeah, I'm not sure we entirely fully understand how all of that gas gets completely there in the first place. So, again, there's still lots of kind of holes in that theory. So there's there's again, as with so many things I've said tonight, there's still work to be done to understand that.
Yeah, we also got a question here about red supergiants and hypergiants and things like that. So the question is, I think, two parts. How far away is the closest red supergiant to us? And if there's such a thing as a red hypergiant, so is there something bigger than a supergiant? I think actually,
yes.
I think there are hypergiants. I think when you have like red giants, is usually what you get when you burn other things than hydrogen, or even hydrogen, but not in the core of a star, but kind of in the shell of a star, which makes the star expand a lot. And I think this process happens with various elements. So first with hydrogen, then with helium, then with all the other elements, well, all the elements up to iron. And I think in each time it gets more explosive, so the star gets larger and the phase goes faster. And I think hypergiant is what you call the even bigger ones.
Yes, I mean they're very, very rare to get to hypergiants, and it basically does mean that they are, although they've probably got a decent amount of stuff in them to have ever gotten that big, they're quite large and very low density. Um, that's kind of how you end up classifying those things. So I think they probably are red hypergiants. In terms of what the closest red supergiant is, I don't know. Um,
Yeah,
there
I don't
will
know
be
either.
one, obviously, but off the top of my head, I don't know what it is.
Okay, we got also one comment about asteroids orbiting each other, or like, can there be can asteroids orbit each other, or are they just too light to do this?
Yes, so there's definitely a few cases actually where we've seen this. It's not totally uncommon. I think one of the better known cases is a pair of objects known as Ida and Dactyl in the asteroid belt, but there's certainly a few of those. So again, it's just kind of like having, when we talked earlier about Pluto and its moon Charon orbiting, and they're orbiting both kind of around each other, and probably when two things sort of captured each other, it's probably something like that.
Oh, that's really cool. I didn't know that was possible, so that's nice.
Yeah, yeah, yeah.
Okay, I think that's already our time up. So it's 8 p.m. at my clock. Thank you all for watching. Thank you all for sending us all these great questions. It was great to answer them all. Thank you, Andrew, for answering all the things that I have no idea about and for being here.
No, thank you for having me back.
Yeah,
It's good fun.
we'll be back.
Enjoyed.
We'll be back next Monday again with another live stream where you can ask us all the questions that we have left open this time. And also there are other things going on this YouTube channel, so subscribe if you want to see more. Usually on Tuesdays there's some lecture that about interesting astronomy topics, and just keep an eye out for other things going on here. And yeah, I hope to see you next week. Have a nice day.